Physics Challenge 1, Electrical Characteristics. This question is asking to find the surface charge distribution on the sphere when potential phi is given. Okay, so you know this is a very basic theory. Potential phi r and the charge distribution, they are related, and that's a very basic things you have to remember. The Poisson's equation, okay, this is a fundamental equation for electrical characteristic. The charge distribution function and the potential are related by double integral. Okay, that means if charge distribution is given, then you can find out what the potential at any point in the space. The reverse is when potential is given, then you should be able to determine the charges distribution. But you need a boundary condition, like this one is a conductor with a radius a, and we're talking about outside of this conductor, because inside the conductor has the same potential, so inside it's zero charge. Okay, so with the boundary condition, you integrate the charge distribution to get phi or potential, or you take a derivative of phi to get the charge distribution. So here we have to take a derivative of this. Now let's review where the Poisson's equation come from. You remember that electrical field is defined as gradient phi, right? So this is a gradient equation. Okay, now E epsilon equals D, and divergent D is gonna give, this is Maxwell's equation, the charge distribution. So we go through E, D, and charge distribution. Okay, so divergent, we're talking about polar coordinate here, and r, theta, and phi. This missing one is phi here. So if you take a derivative twice, this become the double triangle. Sometimes you can write this way. Okay, now we take this derivative on this equation. Okay, so you can do step by step, take a derivative once and later twice, or you can do directly this is gonna give you negative rho epsilon. Okay, so charge distribution is obtained by take a derivative. So let's rewrite. Potential a square r minus a to the third r square, right? Okay, so we replace f with phi here. So take the derivatives and multiply r square. So it's going to be minus a cos theta and negative a square r square, and we multiply r square, so this disappear. Negative 2a square, and r to the third we multiply r square, so it's going to be r. So this part is done. Okay, so let's say this is this part, and we do r square, second derivative of this part is going to be this disappear, so it's going to be plus two a to the third r square, right? Okay, let's try this part. We take a derivatives of this, so this is gonna be negative sign, so this will be a sine theta a square r minus a third r square, and this become double the square, and we take this one, we take a derivative again, then this will be we take a derivative of this 2a sine cosine and whatever here, and because of this disappear, and r square, so it's gonna be 2a okay, so this is 4. So we have 2 here, we bring the 2 here, we add this both together, then we know this is gonna go away. Okay, so the 2a, what is remaining, and when you take the divergent at the r equal a, the value here, it's going to be don't forget cos theta, 2a cos theta. Oh, this is negative, so negatives go away. No, negative stay. Divided by a. Okay, so that's right. Okay, so this negative and this negative is cancelled out, so that's gonna be low. But we're asking sigma. The sigma and low is slightly different. What's the difference? Well, this is the density per volume, this is the density per square area. So we have to do conversion. How we convert it? This is related to a cube. This is related to a square. Okay, so we need to take a ratio. The ratio will be, we divide this by this, so it's gonna be 3a, so sigma 3a equals 2a cos theta a. so eliminating this, sigma will be 2 over 3 a epsilon cosine theta. Okay, so this gonna be function of theta. So distribution is a function of theta, depend on the location of theta. It's maximum here and becomes 0. Okay, so because of this distribution, you observe the potential at the distance r here with theta direction, this function. Okay, so if we do opposite, we integrate this, then we should be able to get this one. So that's the basic equation of Poisson's equation, and this is fundamental, even more fundamental than Coulomb's law. We can deduce Coulomb's law from this equation. So this is something like a Newton's F equals ma in the electrical characteristic. You have to remember this. Okay, so the potential, the Newton's F equal ma is actually, instead of F, we can use gravity potential, and we can make similar equation like a Poisson's format. Okay, so I hope you enjoyed this video. If you like, check out the physics video we have, and if you like, subscribe.